Hey gang, welcome back to 4600. Let's go ahead and do the recommended homework solutions for the 5556 homework. I'll try to go through these pretty quick, and I might cut a few corners to at times to not be as in depth on this one. So we'll see where we go. But I will chapter these out like I've been doing, so you don't have to watch them all if you don't need to. All right. So let's get going. So the first question was exercise 5.72 in the book, and it said back in exercise 5.1, which we determined the joint distribution of Y1, the number of contracts awarded to firm A, and Y sub 2, the number of contracts awarded to firm B, is given by the entries in the following table. The marginal probability function of Y sub 1 was derived in exercise 5.19 to be binomial with n equals 2 and p equals to 1/3. Find the expected value of y sub 1, variance of y sub 1, and then the expected value of y sub 1 minus y sub 2. This binomial factor here is kind of nice to know. We could technically use that to find the expected value of y sub 1 if we wanted to, because we could treat it like a binomial distribution in that case. But I'm going to show you how you can do it from the table, because the formula in the book is kind of more important, and kind of wish they hadn't said anything about this being binomial. It's nice to know it's binomial, or that the marginals are binomially, good Lord, I can't even say that word, binomially, there we go, distributed. But we can solve this without all that, by just using the marginal probabilities of knowing certain values of y sub 1 and y sub 2. So part A wanted us to find the expected value of y sub 1. A quick way to do this with this chart is just basically it's akin to what we did back in chapter 3, where we're really concentrating on y sub 1 up here, and specifically the 0 value, 1 and 2 are discrete random variables. And we need to multiply 0 times each one of these things, 1 times each one of its probabilities, and 2 times each of those, and add them together. A quicker, simpler way to do that would be the following. Sum up the columns, probability values, like that, and then just think about it as 0 times the marginal probability that y sub 1 equals 0. So it would be 0 times p sub 1 of 0 plus 1 times p sub 1 of 1 plus 2 times p sub 1 of 2. All right, which is just 0 times 4/9 plus 1 times 4/9 plus 2 times 1/9, which should give us an expected value for y sub 1 of 2/3. All right. I'm going to go ahead and just state this. You can do the same thing with the rows to find the expected value of y sub 2, which we're going to need in part C anyway. And so similarly, you could do this as 0 times p sub 2 of 0 for the random variable y2 plus 1 times p sub 2 of 1 plus 2 times p sub 2 of 2. And we're going to end up getting the same thing, because this first row column is 0 times 4/9, 1 times 4/9, and then 2 times 1/9 is the row column. So it's going to be the same thing. So we get 2/3 there as well. So that actually makes part C pretty easy for us. But that's how you can answer it without even worrying about the binomial aspect of y sub 1 or y sub 2 respectively, as far as the marginal distributions are concerned. All right, so that's part B says find the expected value of y sub 1 squared, which is a similar process to, or actually it's not that. We need to find variance of y sub 1, but we need the expected value of y sub 1 squared. So to do this by hand using the table, we can do 0 squared times the probability of the y sub 1 column plus 1 squared. So we're just squaring the random variable here, p sub 1 of 1 plus 2 squared times p sub 2 of 2, or p sub 1 of 2, sorry. And that's just 0 times 4/9 plus 1 times 4/9 plus 4 times 1 over 9, and we end up getting that the variance is 8 over 9. Now, if we'd use the fact that the binomial was here, we wouldn't have gotten that value there. What we would have gotten for the variance, though, would be variance of y sub 1, is equal to the expected value of y sub 1 squared minus the expected value of y sub 1 quantity squared, which would just be, we take that 8/9 minus 2/3 squared, and that should give us 4 over 9. So the variance is the actual answer there. I'm not going to keep this on the page, but to answer this using binomial, remember for the binomial distribution, the variance, or sigma squared in that case, is n times p times q. Remember, q is 1 minus p. So n in this case was 2, p was 1/3, and q is 2/3. So if you multiply that together, you get 4/9 as well. So that's a quick shortcut to doing that in this particular problem, but you're not always going to know what your distribution is. And so I wanted you to see how you would do it just using the table of probabilities you have sitting in front of you. The last one, part C, is now easy to do because of what we did in part A. So C just asks you the expected value of y sub 1 minus y sub 2, and that's just equal to the expected value of y sub 1 minus the expected value of y sub 2, which is going to equal 0 because both of them are the same. 2/3 minus 2/3 equals 0. So the expected value, when you subtract those from each other, is just nothing. All right, so that's 72, and we'll move on to the next one in a second. Okay, 5.74. So referring back to exercise 5.6, 5.24, and 5.50, suppose that a radioactive particle is randomly located in a square with sides of unit length. Okay, a reasonable model for the joint density function for y sub 1 and y sub 2 is as follows. It's actually a uniform distribution. 1 when y sub 1 is between 0 and 1, and y sub 2 between 0 and 1. So they want us to find a bunch of different things here. They want us to find what is expected value of y sub 1 minus y sub 2, the expected value of y sub 1 times y sub 2, and then the expected value of y sub 1 squared minus y sub 2 squared, and then finally what is the variance of y sub 1, y sub 2. So there's a little bit of work in here, but at least the integrals are easy to do. And so we're going to answer part A and B on the first slide here, solution slide. So part A, they just wanted to know what was the expected value of y sub 1 minus y sub 2. There's more than one way to do this, but I'm going to go ahead and find the expected value of y sub 1 and y sub 2 separately. So we're doing double integrals from 0 to 1, 0 to 1 of 1 times y sub 1, multiplying that extra variable in there, dy sub 1, dy sub 2. Alright, so we'll get the following. Zero to 1 dy sub 2, so that's the integral there. So we end up integrating 0 to 1 of 1/2 dy sub 2, which just equals 1/2 times y sub 2, value weighted from 0 to 1, so we get 1/2 as the expected value of y sub 1. Expected value of y sub 2, I think, comes out to be the same thing, probably because this function, the random variables are independent in this function, so we end up getting the same thing. And obviously we're going to integrate this with respect to, I probably should have done y sub 2 first to kind of get that out of there, but it doesn't matter. I'm going to continue on where I've got. So I'm going to 0 to 1, that's going to be y sub 2 times y sub 1 from 0 to 1 dy sub 2, 0 to 1 y sub 2 dy sub 2, which just equals 1/2 y sub 2 squared evaluated from 0 to 1, and indeed we get 1/2 for that as well. So lo and behold, the exciting answer and conclusion to this is the expected value of y sub 1 minus y sub 2 is equal to the expected value of y sub 1 minus the expected value of y sub 2 separately. And we get 1/2 minus 1/2, or just 0 for the answer there. I'm pretty sure that a lot of these that we're getting 0 when we do the expected value of y sub 1 minus y sub 2 is due to the fact that these functions, the functions that are independent, end up having the same expected value for y1 and y2. So those values are y sub 1 and y sub 2. And so therefore, they just cancel each other out when we try to find the difference. Nonetheless, you know, it doesn't always end up that way. But in the cases where, like this, some of the problems we've seen, that does happen a little more often than we would like to see. But it's just an average. So on average, you're going to get a value of 0. All right. Now the second part wanted us to find the expected value of y sub 1 times y sub 2. So I'm going to set up my double integral again, 0 to 1, 0 to 1. I got to multiply in y sub 1, y sub 2. I mean, it's just times 1, so I'm going to leave that out. Times the function. All right. And so I end up getting 0 to 1 with respect to y1. I get 1/2 y sub 2. Y sub 1 squared evaluated from 0 to 1 dy sub 2. And which is just the integral from 0 to 1 of 1/2 y sub 2 dy sub 2, which equals, we're going to get getting 1/4 y sub 2 squared evaluated from 0 to 1, which just equals 1/4. So that one wasn't too bad. This is pretty simple. When you have a uniform joint distribution function like this one, the integrals are way easy, so that's a good thing. Part C, we needed to find, we're looking for the expected value of y sub 1 squared plus y sub 2 squared, but we probably need expected value of y sub 1 squared and y sub 2 squared separately, because we don't want to throw those in the mix, although we could. Matter of fact, we're going to try this. I'm going to try a different approach and see if I get the same answer. I should. So if I wanted to find the expected value of y sub 1 squared plus y sub 2 squared, I could do the following. I'm still going to double integrate from 0 to 1, 0 to 1. I'm going to multiply in y sub 1 squared plus y sub 2 squared times 1 dy sub 1 dy sub 2. I'm working with that in net here. Let's see how it goes. So if I do the inside integral first with respect to y sub 1, then that y sub 1 squared would become 1/3 y sub 1 cubed plus y sub 1 times y sub 2 squared, and all that's got to be evaluated from 0 to 1 dy sub 2, which equals the integral from 0 to 1. If we plug in 1 every ratio of y sub 1, we get 1/3 plus y sub 2 squared dy sub 2. All right, and then now integrate that with respect to y sub 2. We get 1/3 y sub 2 plus 1/3 y sub 2 cubed. 1/3 y sub 2 cubed from 0 to 1. And that just gives us 1/3 plus 1/3, which equals 2/3. So those special theorems where you could split these out really wasn't necessary here. We could have actually gotten away with just throwing in the y sub 1 squared plus y sub 2 squared. It didn't really make anything that difficult here, and that's something you can do. The way I did it on my notes is that I did find expected value of y sub 1 squared and then found expected value of y sub 2 squared, but those ended up just being these two values right here anyway. And when you add them together, you get the same thing. So if you did it that way, that's fine. That works. Both ways work. So for part D, the last one, they wanted us to find the variance of y sub 1 times y sub 2. We have the expected value of y sub 1, y sub 2, which was this dude right here, right? We're going to need that in a few minutes, but we need the expected value of y sub 1 squared times y sub 2 squared. That's what we're missing. So we need to find that first, times y sub 2 squared. So we're double integrating again from 0 to 1, 0 to 1. And we don't need to use a special theorem here. We're literally just going to throw in there y sub 1 squared, y sub 2 squared times 1, dy1, dy sub 2. And integrating the inner integral for y sub 1, we get 1/3 y sub 1 cubed, y sub 2 squared. And that's going to be evaluated from 0 to 1 dy sub 2. Which just becomes, plugging in for y sub 1, we just get 1/3 y sub 2 squared. So the integral 0 to 1, 1/3 y sub 2 squared dy sub 2. And finally, that's going to equal, we end up getting y sub 2 cubed over 3. And so 1/3 times 1/3 is 1/9. And we're going to evaluate y sub 2 cubed from 0 to 1. Which just gives us 1/9. So that's the expected value of y sub 1, y sub 2 squared. So the variance of y sub 1, y sub 2 is equal to the expected value of y sub 1 squared, y sub 2 squared, minus the expected value of y sub 1, y sub 2, all quantities squared. All right, which is just equal to 1/9. Minus, and the expected value of y sub 1 times y sub 2 was 1/4. Square that, and the answer, excuse me, comes out to be 7/144. It's not a pretty variance, but nonetheless a variance. And that is it for 5.74. All right, so the next one's 5.76. So this is a function we've seen before. The functions f of y sub 1 and y sub 2 equals 4y sub 1 times y sub 2, where y sub 1 and y sub 2 are both between 0 and 1. So they just want us to find the expected value of y sub 1, the variance, and then the expected value of y sub 1 minus y sub 2. So we should be able to do A and B pretty quickly on the first slide after this one. So part A just wants us to find the expected value of y sub 1 here. And that should equal the double integral. And again, the limits were nice here. We don't have any constrictions here. So it's 0 to 1, 0 to 1, 4y sub 1, y sub 2, times y sub 1. We're multiplying an extra y sub 1 in there. dy sub 1, dy sub 2. Which just equals the double integral from 0 to 1, 0 to 1 of 4y sub 1 squared, y sub 2, dy sub 1, dy sub 2. And if I integrate the inner integral with respect to y sub 1, I should get the following: 4/3 y sub 2, and then we're going to evaluate y sub 1 cubed from 0 to 1, dy sub 2. Which is really just the integral from 0 to 1, 4/3 y sub 2, dy sub 2. All right, and that just cleans up to become, once we integrate that with respect to y sub 2, we end up getting 2/3 y sub 2 squared, evaluate from 0 to 1, which means that we get 2/3 units here as the expected value. It's not too bad. Part B, we need to find the expected value. We need, before we can find the variance, we need to find the expected value of y sub 1 squared first. So again, it's a similar integral, except for we're going to multiply in a y sub 1 squared as the extra one. So when I do that, it should become 4y sub 1 cubed y sub 2 after multiplying in that extra term. Now let me just write that out. 4y sub 1, y sub 2 is the original function, times y sub 1 squared, dy sub 1, dy sub 2. And so then that'll clean that up here. Alright, cool. So now we can do the integration. So the inner integral with respect to y sub 1 will become y sub 1 to the 4th over 4. So that's going to clean this up to just be y sub 2 times y sub 1 to the 4th where we're going to evaluate the y sub 1 to the fourth from 0 to 1, dy sub 2, all right, which is just the integral 0 to 1 of y sub 2 dy sub 2, which is 1/2 y sub 1 squared, and we're going to evaluate the y sub 1 squared from 0 to 1, so we end up getting 1/2 as our y sub 1 squared, or units squared. All right, so finally we can find the variance. Again, we should know the formula by now. Which turns out to be 1/2 minus 2/3 squared, which is ends up being 1 over 18 when you simplify that, units squared. All right. So now we can do part C, which was finding the expected value of y sub 1 minus y sub 2. Since we already have expected value of y sub 1, we know that to be 2/3. I think we've proven this to be independent before, so we could kind of cheat and go, yeah, of course, expected value of y sub 2 is 2/3. But, you know, it is sometimes important to show these things. So just calculate it really quickly. Expected value of y sub 2 is the integral 0 to 1, 0 to 1. I'll go through this fast. I won't even talk through it. And it does. It turns out to be the same. So therefore we know what the expected value of y sub 1 minus y sub 2 is going to equal, because inevitably we just take those two values separate and subtract each expected value from each other. That's 2/3 for expected value of y sub 1 minus 2/3 expected value of y sub 2, so you get 0. Cool. All right, well, we'll do the next problem in just a second. All right, the next one's 5.79, and they kind of gave us a diagram. They didn't give us an actual function here, but the thing to note here about this problem is the word uniformly distributed. When you see that, you're going to assume that the PDF of this function is got something to do with f of y sub 1, y sub 2 equals 1 with these limits set up for us, okay? And they just want us to find the expected value of y sub 1, y sub 2 in this case. This can be done pretty simply in a simple integral. The things we have to take account of is what these two lines here represent. So you can either write this as y sub 2, sorry, write that a little bit clearer, y sub 2 equals 1 minus y sub 1. Conversely, you could also write that as, y sub 1 equals 1 minus y sub 2, which will come in handy when we actually do our integral. And this one over here is y sub 2 equals y sub 1 plus 1. All right. Actually, hold on a second. Yeah. Yep, that's correct. Because if I plug in -1, I get 0. If I plug in 0, I get 1. Or the way we might want to write this when we do the integral in a minute would be in terms of y sub 1 equals, it's going to be y sub 2 minus 1. Alright, so that's the other way we can write it. The reason I'm doing this is because there's a couple different ways to do this. You could find the area of just this triangle here and then find the area of this triangle over here, but it's pretty symmetric, and I don't want to do two integrals. I just want to do one. And so I kind of want to go in the y sub 1 direction first, and since we're borderlined by a diagonal line here and a diagonal line here, I want to set up my integral over y sub 1 with respect to those two lines. And so I need them to be in terms of something involving y sub 2. All right. So the expected value of y sub 1, y sub 2, or times y sub 2, is equal to the double integral. We'll set that up first. And since I said the problem said this was a uniform distribution, it means everything's at the height of 1. So the function's just 1. So it's really y sub 1 times y sub 2 times 1 dy sub 1 dy sub 2, because I want to go in the y1 direction first. So since I'm going from here to here, my inner integral is going to go from y sub 2 minus 1 to 1 minus y sub 2. All right, so I'm basically using this guy to this guy in the y1 direction. All right, and then for the outer integral, we can just go from 0 all the way up to 1, since we've already taken care of the slanted sides in the first integral, or the inner integral. All right, so I'm going to change colors from here on out. So this is going to equal, the outer integral is going to be 0 to 1 still. The inside integral, if we do it with respect to y sub 1, is going to be 1/2. We get a y sub 2 still there. Those are the constants. And then we're concerned about y sub 1 squared, evaluated from y sub 2 minus 1 to 1 minus y sub 2 dy sub 2. All right, so this isn't as sweet and nice as some of the other ones we've dealt with. So this outer integral is still 0 to 1. I got 1/2 y sub 2. And then inside here, I'm going to get 1 minus y sub 2 quantity squared minus y sub 2 minus 1 quantity squared. Okay. Turns out that this is kind of not going to be so bad. We're going to get a pretty simple answer here in the end of it. We get that 1/2 y sub 2 is here, and then if inside the brackets here, if I kind of expand both these terms, the first one is going to be 1 minus 2 y sub 2 plus y sub 2 squared minus, we get y sub 2 squared plus, minus 2 y sub 2 plus 1. All right, and dy sub 2. But if we start looking at that before we move to the next step, we got 1 minus 1 essentially, so those cancel. We got negative 2y sub 2 minus a negative 2y sub 2 becomes negative 2 plus 2 essentially, so those cancel. And then lastly, I got y sub 2 squared minus y sub 2 squared, which those cancel, so this all becomes 0. How nice. How nice was that? So we're really integrating 0 to 1, 1/2 y sub 2 times 0, which is just equal to the integral of 0 to 1 of 0. And you can't really integrate 0, can you? So the answer to this is 0. If you did this in parts, you would have gotten the same answer. Like if you, for example, if in this equation here, if you had decided you wanted to go in the y1 direction first, you have to go from here up to here, and then from here to here in one integral. Call that call that area A, and then area B over here, you'd have to go from here up to here and here over to here, and to get those two. But once you added them together, you'd find out that you got 0 as well. So it just means that on average we would get a value of 0 in this instance. Okay, when we multiply y sub 1 times y sub 2. That's all there is to that one, folks. All right, last one, gang. Exercise 5.80. In this one, we got in exercise 5.16, which I think we played with a little bit in a previous example or exercise. Y sub 1 and y sub 2 denoted the proportions of time that employees 1 and 2 actually spent working on their assigned tasks during a workday. The joint density of y sub 1 and y sub 2 is given by little f of y sub 1, y sub 2 equals y sub 1 plus y sub 2, where y sub 1 and y sub 2 are between 0 and 1. Okay. Employee 1 has a higher productivity rating than employee 2, and a measure of the total productivity of the pair of employees is 30 times y sub 1 plus 25 times the random variable y sub 2. Find the expected value of this measure. Basically, what we want to do is find the expected value of 30 y sub 1 plus 25 y sub 2. So we're finding the expected value, we can bring the constants out of there and separate the expected values a piece. So we can do 30 times the expected value of y sub 1 plus 25 times the expected value of y sub 2. That's what we really want to find. So we need expected value of y sub 1 and y sub 2 is essentially what we need in the long run. So does this create some work for us? Sure it does. We could multiply that entire function into the integral. You got to be really careful with your arithmetic there. Is the only thing I would caution for not doing that. I prefer just to find the expected values separately, just in case I need them for another part of a problem somewhere. It's something I won't have to do again. So to find the expected value of y sub 1, we're going to integrate. We don't have any restrictions other than that we have to between 0 and 1 for y sub 1, and the same thing for y sub 2. So I'm going to go 0 to 1, 0 to 1 either case. And I'm going to throw in the y sub, our function was y sub 1 plus y sub 2, but we've got to multiply in there a y sub 1 variable. And that's going to be times dy sub 1, dy sub 2. Which just is the double integral of y sub 1 squared plus y sub 1 times y sub 2 dy sub 1 dy sub 2. So now we just got to integrate this thing. So the first step here, the integral, we end up getting the following. I get 1/3 y sub 1 cubed, or excuse, y sub 1 cubed, yes, plus 1/2 y sub 1 squared y sub 2, evaluated between 0 and 1 dy sub 2. Sorry, I ran out of room there. Which equals the integral from 0 to 1 of 1/3 plus 1/2 y sub 2 dy sub 2. And that's not too bad to integrate there. We get 1/3 y sub 2 plus 1/4 y sub 2 squared between 0 and 1. And so we end up just getting 1/3 plus 1/4, which turns out to be 7/12. Right? Turns out, even though this one's probably not, I think we proved that this one once before it was not independent, that they were dependent on each other. But it turns out the expected value of y sub 2 turns out to be almost exactly the same thing, or exactly the same outcome, even though it's a different look, slightly different look to it. Times, now we got to multiply this by y sub 2. Alright, which equals 0 to 1, 0 to 1 integral of y sub 1, y sub 2 plus y sub 2 squared dy sub 1, dy sub 2. Which equals, outer integral still there, inner integral with respect to y sub 1, we should get 1/2 y sub 1 squared y sub 2 plus y sub 1 times y sub 2 squared from 0 to 1 dy sub 2, which cleans up rather nicely to 1/2 y sub 2 plus y sub 2 squared. So it's kind of like just the flip-flop of the thing we got before, dy sub 2, which just simply equals 1/4, hold on a minute, this is supposed to be y sub 1 squared. Oh no, it's just supposed to be y sub 2. So yeah, that becomes 1/4 y sub 2 squared, brain fart for a moment, plus 1/3 y sub 2 cubed from 0 to 1, which just equals 7, which is going to end up equaling 7/12 as well. So we've got those two pieces. So now we can find the expected value of 30y1 plus 25y sub 2, which is just 30 expected value of y sub 1 plus 25 times the expected value of y sub 2. And so we end up getting 30 times 7 over 12 plus 25 times 7/12, which should just end up giving us something like 385 over 12, or approximately 32.08, whatever their productivity rating is. I don't know if this is a percentage or what. They didn't really tell us that in the problem, so they just said that the total productivity of the pair is this. So I don't know if that's supposed to represent a percentage or not, so we'll just say units. Alright, so that is it, folks. If you got any questions, please holler at me, and we'll see you next time.